Okay, welcome back. This video is going to be on trying to relate circles, let you know what chords are, and then try to talk about the intersecting chords theorem. Now, in grade 10, you don't really hear much about theorems, but there are certain properties which come from theorems which are super useful to us. And that's what I'm going to talk about in this particular video without necessarily proving anything, but I'm going to make you think a little bit of where some of this idea comes from. So first of all, in circles, if you, let's say randomly, now I have already placed points on a circle. Now it doesn't really matter where the points are. You can erase them and put new points on. If you want to create a chord, so a chord is nothing else but simply connecting 2 points on a circle together. And I can do that here. I'm going to just arbitrarily, let's say I'm going to connect these 2 points. That is a chord. And you can take any other 2 points that you like, connect them, and you'll have a chord. So here is one chord. And I can connect the other ones. Here's another chord. Great. Now, interestingly enough, if you have 2 chords, they can intersect inside a circle. Now, they can also intersect outside a circle because they don't have to always intersect inside, and I'll show you how that can happen shortly. Now, with these 2 chords, notice that there is an intersecting point. I'm going to put this point right here. Now we could find it, I guess. If we really wanted to, we can plot this out. Then I'll do a little example later on in this video. Now, the intersecting chords theorem is very interesting. And what happens is that when you have 2 chords that intersect each other, and I'm going to label these line segments. So let's say this first line segment, let's call this A. Okay, so that's A right there. And then that A is simply going, from here to here. So that's my A. I'm going to put B, so let this be B, and then B would be from this point to this point. So that's B. And I can do the same thing for the other chord. So I'm going to label this one as C, and then I'm going to label this one as D. What this intersecting chords theorem states, and it's pretty neat that we can use that, it says that the multiplication of the line segments of the chord, so for example, this A multiplied by this B right here, is equal to the multiplication of the other 2 line segments which create the chord. So this is going to be C and this is going to be D. Now you might say, how in the world does this come about? Now if you've studied similar triangles ever, and you should study them at some point, and you will be studying them in grade 10 a little bit later, I guess, if you're doing that, but I'll give you a little bit of a hint. So similar triangles basically have the same angles, but they don't necessarily have the same sides. If 2 triangles have exactly the same sides, then they're equivalent, right? Then they're equal. We call them, they're congruent. But if they only have the same angles between each other, so those 2 triangles, and maybe the sides are different, then those are called similar triangles. And if you have similar triangles, then there is a nice ratio and proportion between the sides. And that's what this intersecting chords theorem uses, because it turns out that the triangle, and I'm going to kind of nicely draw it out here for you, nicely, I guess as nice as it comes. So let's say this was your triangle right here, first one, and then you have this one, which is created right here. So this would be your second triangle. Right there, it turns out that these 2 triangles are similar to each other. Now, visually, you can kind of even see that they're similar to each other. And that's the beauty of having these points on the actual circle. And it only happens because they are actually on the circle. So it's a nice property within these circles that we have. And because these two triangles are similar, then we can have this nice property right here, which is just the intersecting chords theorem. Now, what happens if you have, let's say, let's say arbitrarily here now, or purposely, so I already put 2 points here, and then, I don't know, I'm going to put I guess another point here, let's say another point here. If I connected these two and created a chord here and then created a chord right there, then notice that they don't intersect, right? At least they don't intersect inside the circle. However, if I extend, okay, so these lines, I'm going to extend them out, and you'll notice that they will intersect, except they'll intersect outside. So here it is. So they intersect at some point right here. Now, do we still have this same particular property? We do, but you have to be careful a little bit, because, so here what I'm going to do is I'm going to show you that now your A, so your A is going to be all the way to that intersecting point. And that's what happened here, right? Our A was basically to the intersecting point, and then our B was from the intersecting point to the other side of the circle. So here, this is my A. So in that green, that's my A. Your B, the distance of B here, is actually going to be from here to here. That's your B. And I'm going to label this, I'll keep the colors in there so that you can see that. So that is your A and that is your B. And if you multiply those, so if you say A times B, it's going to be equal to the other, so let me go back here. So this would have been your C, all the way to that intersecting point. That's your C. And then for your D, that is from here to here. And this would have been your D. And this, okay, still holds. And again, that's going to be from something which is similar to this idea. Now, you might say, why in the world would I need this? Well, there are actually some applications which are pretty neat. And if you continue on, I do a test for this particular chapter. And so you can go to the playlist and then you'll find the test on basically kind of line segments, triangles, circles. And one of them is trying to create an arch of a bridge. And it asks you, and you can use this particular theorem to find the radius of the circle that creates an arch, which is pretty neat. So you'll see that in the test. And once the test comes out, I'll try to put up a link up above, all right, to that particular test so that you can see the application to this. Now, let's see this thing in action. So what I'm going to do is, let's try to not necessarily prove it, but let's take a circle. Let's put 4 points on that circle. And then once we have those 4 points, we'll create the chords. And then we'll see if this actual theorem works. So I'm going to do it in kind of fast forward motion to create our I'll create a coordinate system and then the circle, and then I'll be right back. All right, so welcome back. So here's your circle. It has a radius of 4, and here's our equation of the circle that we have. X squared plus y squared equals 4. Notice it's centered around 0, so our vertex is basically 0, 0 that we have. And now I want to be able to, let's say, create 4 points. So I'm going to just kind of arbitrarily take the 4 points. I'll do the first one to show you how to put up a point on this circle, and then I'll do the other 3, and then we'll try to create the chords. So one of the points, just out of, okay, so let's say, let it be x is equal to 3. So x is equal to 3. So I'm going to substitute x is equal to 3 in here. and then I'm going to solve for my y, which is basically going to be somewhere right there. But I want to know that value exactly. So if I substitute that in there, so I'm going to get 3 squared plus y squared is equal to 4 squared. And then of course we're going to bring this over to the other side. So this is going to be 4 squared minus 3 squared. And then we're going to take the square root so that we can solve for our y. And that's going to give us, so 4 squared minus 3 squared is equal to, now if you take the square root of that, then this is going to be plus minus, right? Because on your circle, you can have the point right there, or you can have the point right here. They're just going to be the same points, except one is positive, one is negative. So now 4 squared minus 3 squared, so I guess it's 16 minus 9. So 16 minus 9 is going to be what, 7. So this is going to be, so this point is square root of 7. Now, yes, unfortunately we do get a radical, and then, radicals, unless it's a perfect square, so it's going to be an irrational number. And because of that, it goes on forever and it has no repeating pattern, so I'll leave it as the square root of 7 here. So that would have been, let's say, 1 point on the line. Now I'm going to find 3 other points on the line. I'll do that in fast forward motion so that we have all our points. So my first point is going to be 3 square root of 7. Now let's find the other 3. I'll do those arbitrarily. All right, we'll see you right back. All right, so welcome back. So here are the 4 points that we have. So 0, 4, 3, square root of 7, 1, negative square root of 15, negative 2, and negative square root of 12. So those are the points. Now the square roots are there because of the fact that it is a circle. And so you're going to have these radicals in there. Now to make our life a little bit easier, you can keep the radicals, but I'm going to kind of take the square roots, and then I'm going to round it to a certain number of decimals, and then it's going to make my life easier to create the actual lines. Because what I need next is the lines, so going from 0, 4 to 1, negative square root of 15. So I'm going to take that chord, find the actual equation of that line. Then I'm going to take the equation of the other line so I can find the intersecting point. That intersecting point, once I have that, then I can create those line segments and find out the lengths of them. So that A, that B, and that C that you actually see there on the diagram. So I'm going to first find the line, equations of the line, and then we're going to find the intersecting point. So I'm going to see you right back, and I'll do that in fast forward fashion. All right, so welcome back. So here are the lines. So the one here in that you see, so that's the actual line. Here's the approximation. So I took out that square root of 15 there for that slope, because the slope is very ugly if you leave it that way. So this gives you an approximation of that line. And that was for the point 0, 4 and 1, negative 15. So that was this one. That is, so let me highlight it here for you again, a little bit bigger. So that's that line. All right. And then the other line that you see, so there it is. So you have it right there. And notice the slope is around 1.222, and then the y-intercept is negative 1.0202, which should make sense. So notice that the y-intercept, which is falling somewhere around there, all right, which is negative, and then the slope is positive, so it looks like it's aligning. Now, once I have these two lines, I have to find the point of intersection. So I'm going to do that point of intersection, and once I find that point of intersection, then we can find the actual chords. All right. So I'm going to graph these two. You can use whatever you like. You can use the process of substitution, elimination, or whatever. I'm going to graph it so that we can visually see that intersecting point. All right, so see you right back. Okay, so here's our point of intersection, and it's an approximate point of intersection between those two lines. So it's 0.552 and then minus 0.3457. Now, for good measure, let me just graph the actual circle as well. Equals 2, this was 4 squared. And so if let me do that circle there. So notice, so this is exactly how these chords look like. So now we want to be able to find the distance. All right, so these are the distances that we will be looking for. And then we can do that intersecting chord theorem. All right, so let me find those distances so that I now know the points. I just have to find the line segment, so that distance, the length of that. And then, so I have to find 4 of them, and then we'll multiply them together to see. All right, so see you right back. All right, okay, so that was torture. If you're doing it, it's going to take you quite a long time. Now, so what I ended up doing was, okay, so here is the circle. Those are all the different points. And now I wanted to find all the line segments and the length of them. So here was, the first one. So that's A. So that's what you see right here. It is being rounded there. Here is your, let's say, B, so that's your B right here, and there's your B right there. So it's 3.5553 and so on. And then I did the same thing. So I did the same thing with C, so that you would have, so C right here, that was from here to here. That's your C. There we have it. And then finally I did the same thing for D, so to find all of those lengths. And once you have that, so here it is. So here's your A times your B equals to C times your D. And notice that this is what you will get. So indeed, they're equal. Now, it's extremely painful, but I think this exercise is super neat because it will force you to understand, like, what do you have to do in all the different steps. So going all the way back, so sure, here is your intersecting chords theorem, and it says AB equals to CD, and it's all nice and fancy. But once you actually do a full-out example, you can see the power of it, and then also see how difficult it is and the number of steps that you would need. And because you're dealing with circles, and of course circle, the radius of it, and then you're dealing with a lot of irrational numbers and radicals, it becomes a headache. All right, so this is it for the video, an extremely, long one, although I fast forward a lot of the different components. I hope that you found it useful, and we'll see you at the test for this chapter. Bye, everybody.